So looking at another example here of power factor correction, and once again we are dealing with a motor in this case. Now in this case we are not given the FLA of the motor, but we are given some other values. We're given its voltage, it's a 575 volt motor, it's a 70 horsepower motor, and we're given the efficiency as well as the power factor. So when we're talking about the horsepower motor, that refers to the true power output. So the mechanical, actual physical work. But that is not the power input to the motor. And the power input to the motor is what we have to put on our power triangle. There's other losses within this thing that all happen in order to make this motor operate. So we're going to go ahead and start looking at our motor here, and we're going to use some of our previous information that we've learned in the past here and determine the power output, and then we're going to convert that to power input. So power output is going to be 70 horsepower, and we're just going to convert that to watts. There are 746 watts for every 1 horsepower. So I multiply 70 by 746, and the power output in watts is about 52,220 watts. All right. Now back from efficiency. Efficiency is equal to power out over power in times 100. So if I want to figure out the power input, I just take my power output and I divide it by my percent efficiency. So in this case it'd be 52,220 watts, and I divide it by my efficiency of 0.9, so 90%. So that's going to come to about 58,022 watts. So the power input, that's what's required on my power triangle for my motor. The true power, that's the input power, and that's what we have to put on our power triangle. So 58022 watts. Now this power factor of this motor is 0.7. So we can use our power factor formula, that is P of the motor over S of the motor, is going to be equal to power factor, but we're going to use it backwards. So I'm just going to swap those two values, take my true power, divide it by 0.7, and I've got an apparent power of this motor of 82,889. Now the quadrative power of this motor, the lagging VARs it requires to operate, we can use Pythagorean theorem. So S of the motor squared minus P of the motor squared, and square root that, and it should come to about 59,195 VAR. All right. So we can keep the true power of the motor. That becomes the total true power of the circuit. That's what's doing the real work, and that's the part that we cannot really manage. So P total is the power of the motor, 58,022 watts. We know that we want to correct this to 0.95. So if we go ahead and solve for the other sides of these triangles, the S total, the new S total, will be our power total of 58,022 divided by 0.95, and so it's going to work out to about 61,076 VA. Using Pythagorean theorem, I can take my S total squared minus my P total squared and square root that all, and that's going to come out to about 1,971 VAR. Okay. So now it's time to determine our QC total, our total leading VARs coming from our capacitor bank. So we're going to take our Q of our motor and subtract off the value in the Q total down here. And the leading VARs that are required of this capacitor bank is about 40,124 VAR. So about 40 kVAR bank. Three-phase bank. Okay, let's go ahead and now we're going to solve for the capacitance in each phase. So in order to do that, we need to figure out our VARs per phase. So our QC per phase, or in the phase, will be equal to our QC total divided by 3. So that will come to 40,124 divided by 3, and you're going to be about 13,375 VAR per phase. In Y, this is where we have to determine the connection, because this is where the formula changes. So, or what value we use changes, I should say. So in this case, we have to know the phase voltage squared and divide it by our Q per phase from our capacitor bank. In this case, because it's connected in Y and the line voltage is 575, I'm going to have to determine my phase voltage, V line, divide by root 3 to determine the Y phase voltage. Should get about 331.98 volts. So we can go ahead and sub that in. Our phase voltage, if the capacitor bank is in Y, 331.98 volt squared divided by 13,375 VAR. And that works out to be about 8.24 ohms. Figure out what that is in capacitance. So that would come out to be, assuming it's a 60 hertz circuit, should probably put that on here at 60 hertz, 321.91 microfarads. All right, so you'd have to buy 321.91 microfarad capacitors and then connect them in Y and put that in parallel with this motor to correct the circuit to 0.95. So if we're in delta, well, we know the phase voltage is the same as the line voltage. So our XC is going to be equal to our phase voltage squared over our QC of the phase. So it's a 575 volt motor. So that's our line voltage, same as our phase voltage. Square it and divide it by our 13,375 VAR. That comes to about 24.72 ohms. Basically 3 times the opposition as it was in Y, 3 times greater XC. And converting that to capacitance using our 1 over 2 pi FXC formula, you're going to work out to be about 107.31 microfarads. So in delta, it's 107.31. So just remember that relationship again. It's about the third the size of capacitance if it was in delta than in Y. I guess one other question, what would be the new total, I guess we could say, what would be the currents of the motor and what would be the new total current? So what would be the current here? And so that'd be the current of the motor. And what would be the current of the circuit in this case? Well, the current of the motor, or current without power factor correction, we could use our I line of the motor. Motor equals S of the motor divided by V line times root 3. So if we were to punch that in, 82,889 divided by bracket 575 times second function root 3 end bracket. So that motor is going to draw approximately 83.2 amps. So if we didn't have power factor correction, that would be the I total of the circuit. So what would we be after power factor correction? So what would be right here if we put that capacitor bank in parallel? Same formula. The I total would be the S total of the circuit divided by the V line times root 3 in brackets. So that would be 61076 divided by bracket 575 times second function root 3 end bracket. Boom. We're down to about 61.33 amps. So a drop of a little more than 20 amps there on the one motor, which is quite substantial. So hopefully that helps out, and yeah, we'll catch you later.